Okay, guys, so for the answers of this chapter, a lot of it we did cover in class, but I have asked you some questions that are going to make you think. So there's just a few things that I would like to discuss here, some hints to give you. So remember that so our action in naught dimensions was the following. Uh, S was equal to alpha over 2 phi squared. So that was the free piece. And then there was a term which was g phi to the 4. Now, what you can imagine is that each of these terms had associated with it a Feynman rule. So let's think about the alpha over 2 phi squared term, okay? What did this term give us? This term gave us the fact that the line was 1 over alpha. And then when we look at this vertex, this g phi to the 4, what did this give us? Well, this told us that there were vertices that have 4 legs, so that's what the vertex looks like. And this gave us a rule. It gave us minus g times by 4 factorial. Okay? So let's just discuss where this rule actually came from. So remember, the integral that we're calculating looks something like this. There is an arbitrary normalization, and then we had an e to the minus s and some phi to the n. So there was some normalization in integral d phi from minus infinity to infinity, e to the minus alpha over 2 phi squared minus g phi to the 4, and then phi to the n. And if you remember, we separated out the e to the minus g phi to the 4, and then we expanded this. So we had some expansion from m is equal to 0 to infinity, and we had minus g to the m over m factorial, and then we had phi to the 4 to the m, but we expressed the phi to the 4 using the source as d4 dj to the 4 to the m, okay? And this is what we had acting on the source. So strictly speaking here, I should have added in plus the j phi just to jog your memory even more, and added in the plus j phi over here. Now, every time that we drew a dot was associated with the field phi, and that became a derivative with respect to j. So you can see that here, we've got sort of 4 dots appearing raised to the power of m. So each vertex, which is a phi to the 4, comes with 4 j derivatives. And that's why the vertex looks like this, a cross like this, where there's 4 things that I can join lines onto. And they come together, so they're part of one object. Okay, so if we had, and now this is part of the hint, okay, if we had plus lambda phi cubed, let's say, okay, then what would the Feynman rule be for the lambda phi cubed term? Well, in exactly the same way that expanding the e to the minus g phi to the 4 brought down fields in 4s, if we were to expand something like e to the minus lambda phi cubed, we would get, a sum maybe from q is equal to 0 to infinity, minus lambda to the q over q factorial, and now we would get phi cubes. So 3 fields phi, and this is raised, of course, to the power of q, and this would translate into d3, dj3 raised to the power of q. But the important point is now we get fields coming in 3s. So we would invent a new rule where we have 3 legs meeting at a point at the vertex, okay? 3 legs meeting at the vertex. And what would the rule for this new vertex be? Well, it makes sense to say minus lambda because we've got a minus lambda coming each time. Now, why is there this 4 factorial? Well, the 4 factorial, one way to see it is if I were to study this diagram, so let me maybe make a little bit of space. Come on, pen. Okay, there we go. Okay. If we were to study this diagram, this particular diagram has got no combinatoric factors. No combinatoric factors. And that means it must be equal to the vertex. Whatever the rule for the vertex is, it must be coming from this diagram. And the way to see what we get, well, here we have 4 dots, and then we have our vertex. Well, let's connect the first to this dot over here. Let's collect one leg of the vertex. And there are actually 4 ways to do it, because we could have connected to any of the legs on the vertex. And then we can connect another leg to a dot. And the number of ways to do that is 3 ways, because we could have connected any 3 of the legs on the vertex to the second dot. And then we want to connect to one more dot. And now there were 2 ways to do it, because we could have connected either of the legs to the vertex, and then finally we can link up the diagram, and there's only one way to do it. So when we're producing this diagram, we've got 1 times 2 times 3 times 4, 1 times 2 times 3 times 4 ways to do it, and that's 4 factorial. That's the origin of the 4 factorial in this Feynman rule. Okay, so now let's argue exactly the same thing, but now for the cubic term, okay? So sorry, this should have stayed red. There we go, it's red again. So this is now for the cubic term. And what are we going to do? Well, we are going to take 3 dots and connect it to the vertex. Why? Because we look at this diagram. Once again, there's no combinatoric factors, no equivalent lines, closed lines, equivalent vertices, nothing like that, which means this must be equal to the rule for the vertex. Okay, just a little trick to get this. So let's see. So we start off with this, and we've got our cubic vertex. If we do the first step, well, we could have connected any one of 3 legs to that first dot. So there's 3 ways to do it. If we then connect the next line, well, we could have connected any 2 legs of the vertex to this next dot. So there's 2 ways. And then finally, to make the last connection, there's only 1 way to do that. 1 way. So how many, what's the factor associated with this? Well, it's 3 times 2 times 1, which is 3 factorial. So for this vertex, you would take minus lambda times by 3 factorial. So those are the Feynman rules that you would have. You would then invent some combinatoric rules, and those are very similar to what we've already had. So again, factor of 1 over q factorial for q equivalent lines, 1 over q factorial for q equivalent diagrams, 1 over q factorial for q equivalent vertices, 1/2 for every closed line. And then you'd have a set of Feynman rules. And then how would you test them? How would you make sure that you got them right? Well, you would calculate some correlation functions. So in this particular model, write down your set of rules, whatever you think that they should be. You've got a good guess. And once you've got a guess, why don't you compute some things? Compute phi cubed. You could compute phi cubed. You could compute phi squared. You could compute phi. You could compute 1. All of these different correlators. And now it would be in a double perturbation expansion. So for example, if you're computing 1, it would start with a 1. Then there would be a term that multiplies lambda. Then there would be something multiplying g. Then there would be something multiplying lambda squared, something multiplying g squared, something multiplying lambda g, and so on. And then each of these coefficients, you could then try to produce using your Feynman rules. So for example, if you were studying, let's say this term, well, there's one lambda, which means you want one cubic vertex, and there's a g, which means you want one four-legged vertex like that, okay? So if we try to combine these, can we combine these in any sensible way? Well, let's check that. If I try to combine these, maybe I could do this. Let's connect two legs of the cubic vertex to the quartic vertex. Then I can connect one more leg, but there's always one not connected. One not connected. So it seems like there's no way to build diagrams with no dots and a cubic and a quartic vertex. So our prediction is that this coefficient should be equal to 0. That term shouldn't be here. But if we look, for example, at the lambda squared term, well, the lambda squared would be built using two of these vertices. Is there any way to build diagrams using two of those vertices? You bet there is. Okay, we can connect one leg, so we get this. Then we can connect that leg over there and this leg over here. So there are indeed ways of getting these kinds of diagrams. So this vertex should be non-zero. And then calculate what value you get for that vertex, and that'll allow you to check the Feynman rules that you have postulated. And, you know, you don't have to just stick to the exercises that I've given you. You could go ahead and check. Let's say that you added another term. Let's say you added something like, I don't know, let's say the coupling is kappa, and you decide to take phi to the 10 or something like that. Well, what would you guess? So I hope that this is what you would guess for this rule. You would take a vertex now. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 legs. So there are 10 legs. And you would postulate that this is minus kappa 10 factorial. And you could go ahead and work out the Feynman rules now for that vertex. But the point is, after a little bit of playing and working out a few correlators, you should feel confident to write down the Feynman rules for any theory that you can think of. So good luck, happy experimenting, and let's now move on to chapter 16.